Hello, I'm Karl Olson, a PhD student at the University of Colorado Boulder, and today I'll be introducing our work titled Nothing Else Matters, Evaluating IPv6 Access Control Policies and Residential Networks. If you're running an IPv4 network in your home, you're almost assuredly running NAT. For a consumer, this ubiquitous presence provides both a default security posture through NAT's default deny ingress filtering and a common operational familiarity across manufacturers due to the mandatory need for address translation. With IPv6, this standardized behavior is no longer assured. For example, you may continue to operate a gateway in a manner similar to IPv4 NAT using IPv6 translation, or you could have a firewall, or potentially nothing at all. As a consumer, there's no great way to know what's going on or how these changes impact you. Worse, ISPs can enable IPv6 overnight. If your router and devices prioritize v6 traffic, you could find yourself in a position where yesterday your devices were behind a NAT gateway, and today they're potentially exposed to the open internet. One problem here is that RFCs do not precisely define how IPv6 should be implemented within consumer gateways. Instead, they often only provide recommendations that IPv6 be implemented in a way that's familiar to the consumer, i.e. something similar to IPv4 NAT. But how do you implement something familiar for a vastly different protocol, which affords global addressing, the ability to provide end-to-end reachability, and use of multiple address scopes within a single device? Further, there is no specification on whether a device should operate in a closed model, similar to NAT, or with an open end-to-end model. Instead, these decisions are left to the gateway manufacturers to decide. What that leaves us in the best case scenario is that we could potentially have all manufacturers arrive to a single homogeneous operational model for IPv6, defined by possibly firewalls and uniform default security policies. In the worst case scenario, we have no idea what these devices are doing or how they're actually operating. The only way to know for certain is to assess a gateway ourselves, which is an unlikely solution for most consumers. And so in our work, we aim to answer the following two big questions. How do manufacturers reconcile these operational differences that IPv6 potentially introduces? And what are the potential impacts or pitfalls a consumer may experience with IPv6 operation? To do this, we selected 10 commonly deployed gateways and tested them in a real-world configuration within a consumer premises operating IPv6. First, we reviewed and documented the default configuration of each device by assessing the administrative menus, configuration options, and finally their operation. For the operational assessment, we scanned each gateway from two vantages, one from the internal or trusted side of a consumer's network, looking outward, and a second series of scans from an external vantage, connecting inward. Each scan assessed open services, filtering behavior, and overall device response with firewalls enabled, disabled, and under the changes to the various configuration options provided. What we find in our assessment is a diverse range of default configurations and gateway operations surrounding IPv6. Particularly, we find that manufacturers have chosen in a few cases to implement the open model architecture for IPv6 as the default configuration rather than a well-defined firewall, which we mark here at the white circles. In the most egregious example we witnessed, the TP-Link Archer AC1750 provided both a default IPv6 operation while completely lacking any form of an IPv6 firewall altogether. In this worst case scenario, a user's devices would be directly exposed to the internet without any notification, as they were for us. This is also, unfortunately, the top selling router on Amazon.com. A second point of concern we discovered is that when these devices were operated in the open model, both the external and internal interfaces of the gateway were globally addressed and reachable from an external client. Now, typically in an IPv4 NAT network, this internal interface is assumed to operate in a trusted internal boundary and commonly host device administrative portals, hole punching agents, or other configuration mechanisms to ease consumer burden. Now, each of these mechanisms were exposed to the open internet. The methods to implement a refined security policy to address these exposures are challenging at best. For example, some systems provide mechanisms to filter on a per device basis, which captured all address scopes under IPv6 and applied the specified policy. Other devices filter on a per IP basis, leaving to the consumer to recognize that there's potentially many IPv6 IPs available on a system, and that they must apply individual policies for each assigned IP. Now, this could be a near impossible task for devices that generate and use temporary IPv6 addresses on a constant basis. Some systems provide no configuration options at all, relying instead on the manufacturer's default policy alone. In one case, the Ubiquity Amplify router provided no method to modify the system firewall policy. Instead, the only option available was to disable the firewall completely in order to allow access to a device on the internal network. Uniquely, this was the only gateway we assessed that provided a warning to the consumer on the dangers of disabling the IPv6 firewall. All of these unique device behaviors are in stark contrast to the near uniform operational behavior and configuration options found within IPv4 NAT on the same devices. And so what all that means for consumers is that the traditional plug and pray method of gateway operation no longer provides an assured level of baseline security. In fact, the opposite is true, as numerous pitfalls and unintentional exposures exist in the gateways we assessed. With the majority of consumers likely operating their devices in a default configuration, we cannot assume that these users understand the paradigm shift IPv6 provides, or even have the desire to precisely maintain security policies with them. Therefore, it's upon both device manufacturers and standards organizations to quickly address this gap in security. At the most basic level, a gateway should provide a secure default policy for IPv6 that is both familiar and simple to manage. While the IETF provides this exact same recommendation, there is no specified policy to force this behavior. The end result is what we see here, a cursory consideration of IPv6 operation that woefully ignores the impacts that these shifts entail. In future works, we assess the true scale of these exposures through large-scale internet scanning mechanisms for IPv6. Based on our work here, we suspect a number of IPv6 gateways expose consumer networks unexpectedly, leaving many devices open to accessible to the open internet. What is not clear at this time, however, is how consumers will actually respond to these changes under IPv6. We propose a future study to assess both consumer awareness and methods to implement security controls as one method to help establish a common operational baseline and identify mechanisms that are clear and simple for users to operate. We encourage you to further review our paper for additional takeaways and security failures, which highlight the shortcomings of IPv6 operation within consumer gateways. We would now like to open up for any questions that you may have.